Welcome to today's paper reading. Today's paper is titled, OpenELM, an efficient language model family with open training and inference framework. This paper was published on the AR14 preprint by Sachin, Mehta and colleagues from Apple. The OpenELM model employs a layer-wise scaling strategy to optimize parameter allocation within transformer layers, resulting in improved accuracy. For instance, with a parameter budget of around 1 billion, OpenELM shows a 2.36% accuracy enhancement over ALMO, using half the pre-training tokens. To enhance reproducibility, the release includes comprehensive training logs, multiple checkpoints, and pre-training configurations on public datasets. Additionally, code for converting models to the MLX library for inference and fine-tuning on Apple devices is provided. This extensive release is designed to support and expand the open research community, fostering future research initiatives. Table 1 compares OpenELM with other public large language models, LLMs. It highlights that OpenELM achieves a 2.36% higher accuracy than ALMO, a recent OpenLLM, while using significantly fewer pre-training tokens. The table also notes that the average accuracy is calculated across various tasks, which are part of the OpenLLM leaderboard. Models that were pre-trained with less data are marked in gray. Transformer-based large language models are transforming the field of natural language processing. These models, while isotropic, may not efficiently allocate parameters. In this work, the authors introduce OpenELM, a family of models utilizing layer-wise scaling for more efficient parameter allocation. OpenELM is pre-trained and fine-tuned on publicly available datasets, outperforming existing OpenLLMs. For instance, a 1.1 billion parameter OpenELM model surpasses a 1.2 billion parameter ALMO model by 2.36%, using half the pre-training tokens. The pre-training framework is structured around several key components. Firstly, the model architecture is based on a decoder-only transformer, which features non-uniform parameter allocation across layers, achieved through layer-wise scaling. This approach allows for a more efficient use of the parameter budget. Secondly, the pre-training data includes a combination of public datasets such as RefineWeb, Pile, RedPajama, and DOMA, totaling approximately 1.8 trillion tokens. Data is processed on the fly, with filtering applied to exclude sequences shorter than 200 characters or 256 tokens. Lastly, the training process involves 350,000 iterations using the AtomW optimizer, with a cosine learning rate schedule that decays to 10% of the maximum rate. 4 variants of OpenELM are trained, ranging from 270 million to 3 billion parameters. Table 2 provides a detailed breakdown of the datasets used for pre-training OpenELM. The datasets include RefineWeb with 665 billion tokens, RedPajama with 207 billion tokens, and Pile with 411 billion tokens. These datasets are crucial for the model's training and contribute significantly to its performance and accuracy. Figure 1 illustrates OpenELM's performance across various training iterations on standard zero-shot tasks. The data clearly shows that in most tasks, the performance of OpenELM improves as the training duration increases. Additionally, the model checkpoint created by averaging the last 5 checkpoints, which were collected at intervals of 5,000 iterations, demonstrates performance that is comparable to, or slightly better than, the last checkpoint obtained after 350,000 iterations. This suggests that strategic checkpoint averaging can be an effective method for optimizing model performance. Table 3 outlines the tasks and corresponding metrics used to evaluate the performance of OpenELM. Key tasks include ArcC, BoolQ, and Wino Grande, each measured by normalized accuracy or accuracy metrics. This table provides a comprehensive view of how OpenELM is assessed across various benchmarks. In the zero-shot and few-shot settings, OpenELM is compared with several publicly available large language models, LLMs, such as Pythia, Cerebras GPT, TinyLlama, OpenELM, MobiLlama, and ALMO. The accuracy of OpenELM is observed to increase with longer training durations across most tasks. Additionally, the checkpoint obtained by averaging the last 5 checkpoints demonstrates comparable, or slightly better accuracy compared to the final checkpoint. This improvement is attributed to noise reduction through weight averaging. Instruction tuning consistently improves OpenELM's average accuracy by 1 to 2% across different evaluation frameworks using the ultra-feedback dataset. For parameter-efficient fine-tuning, PFT, OpenELM is integrated with methods like LoRa and DORA, showing similar accuracy on average across the given common-sense reasoning datasets. Table 4 presents a comprehensive comparison of OpenELM with publicly available large language models, LLMs, across various evaluation frameworks. The table highlights that OpenELM, chosen as the primary model for this study, demonstrates superior performance compared to baseline models MobiLlama and ALMO, which are pre-trained on public datasets with similar or larger amounts of tokens. Notably, an OpenELM variant with 1.1 billion parameters achieves significantly higher accuracy across multiple tasks, despite using substantially less pre-training data. This underscores the efficiency and effectiveness of OpenELM in leveraging available resources to achieve top-tier performance in language model evaluations. Table 5 illustrates the impact of instruction tuning on OpenELM's accuracy across various model sizes. The data shows that instruction tuning consistently enhances the average accuracy by 1 to 2% across different evaluation frameworks. The models evaluated range from 0.27 billion to 3.04 billion parameters. Key tasks where improvements are observed include ArcSy, HelloSwag, Pika, and Winogrande. This table highlights the effectiveness of instruction tuning in boosting the performance of OpenELM models. The benchmarking of OpenELM models was conducted on two distinct hardware setups: a workstation equipped with an NVIDIA RTX 4090 GPU running Ubuntu 22.04, and an Apple MacBook Pro with an M2 Max SoC running macOS 14.4.1. The evaluation focused on two key metrics: token throughput, measured in tokens processed per second, and the distinction between prompt processing and token generation. Additionally, the total combined throughput was reported. The analysis revealed that the naive implementation of RMS norms significantly impacted the processing time of OpenELM, leading to lower throughput compared to models using optimized layer norm. Future work will focus on optimizing RMS norm to improve inference efficiency. Table 6 presents the performance of OpenELM when fine-tuned with parameter-efficient fine-tuning (PFT) methods, specifically LoRa and DORA, on a common-sense reasoning benchmark. The results show that both LoRa and DORA achieve similar accuracy across various datasets, indicating the effectiveness of these methods in enhancing OpenELM's performance. It is crucial to note that these results differ from those in Tables 4 and 5, which were obtained under zero and few-shot settings using the LM evaluation harness. The exclusion of social interactions QA, SICA, and OpenBook QA, OBQA, in Tables 4 and 5 is due to evaluation issues with the Llama tokenizer in the LM evaluation harness. Table 7 presents benchmark measurements of OpenELM compared to other similar large language models, LLMs, in its class. On CUDA, the evaluation includes OpenELM, MobiLlama, and ALMO, with OpenELM using the Cornet version and the other two using Hugging Face. On macOS, only the MLX version of OpenELM is provided. The key-value cache was utilized whenever supported, and a consistent prompt length of 35 to 36 tokens was used across all runs, depending on the tokenizer. Table 8 illustrates the performance bottleneck caused by normalization layers in large language models like ALMO 1.18b and OpenELM 1.08b. The table shows a significant drop in throughput when using the naive implementation of RMS norm and PyTorch compared to the highly optimized layer norm. While Apex's RMS norm implementation offers some improvement, a notable performance gap still exists relative to layer norm. This data underscores the need for further optimization efforts in future research. In this work, the authors have released OpenELM, an open language model based on the transformer architecture. OpenELM employs a layer-wise scaling method for efficient parameter allocation, leading to improved accuracy compared to existing models. The entire framework, including training logs and multiple checkpoints, has been made open to empower the research community. The project was led by Sachin Mehta, with significant contributions from Mohammad Rastegari and Peter Zatloukal. However, it is important to note that the models are released without any safety guarantees, meaning they could produce inaccurate, harmful, or biased outputs. Therefore, users and developers must conduct thorough safety testing and implement appropriate filtering mechanisms. Thank you for watching.